Okay, so I'm recording now. Let me start a chat box here. I'll make it a big one in case there are lots of comments. I did rewrite section chapter 12. I didn't rewrite every word of it. I just sort of massaged it somewhat, and I put a link to the PDF of the new version of chapter 12 on the class website. I think the main changes are in the first section, which I hope makes things a little bit more a little bit clearer. And since we already went through that, I think I'll just say that that's what I did. So on to general relativity. Here, I tried to clarify the first few sections by adding some things, and I also put a PDF of that on the class website. And the two of the things that I added that I'd like to stress tonight is that general relativity is built upon two of Einstein's ideas. The first idea is that we really have no way of knowing if a particular coordinate system is correct. In particular, it wasn't until the CMB, the cosmic microwave background radiation, was discovered that we realized that the Earth and the Sun and our galaxy were moving relative to what seems to be the basic free-fall coordinate system, or I should say the static coordinate system of our known universe, which some people call a pocket universe, in the sense that it evolved in the view of inflationary cosmology. It evolved from a period of inflation that took a small part of a previous universe into our known universe. Anyway, point is that only when the CMB was discovered did we realize that we were moving relative to the CMB at a certain speed, which of course is now well measured. I can't remember exactly what it is. I hope it's somewhere in the book. If not, I'll have to add it. So that's the first idea. We don't know what particular coordinate system is correct. And so what we should do is we should write our equations as tensor equations. So, and the advantage of tensor equations, as I think we saw last Thursday, and as I hope we'll see again today, is that tensor equations look the same in all coordinate systems. When you transform from one system of coordinates to another, you just have x's in one case and y's in the other, or x's in one case and x primes in the other case. But otherwise, the equations look exactly the same. So the first idea of Einstein then was write everything in terms of tensor equations. The second of his ideas that grew into general relativity is that the physics of special relativity holds inside a sufficiently small laboratory falling freely in an arbitrary gravitational field. So you have an arbitrary gravitational field, but if you're in a sufficiently small lab freely falling in that field, then the coordinates that you would find natural in that laboratory, in those coordinates, you'd say, oh, special relativity applies, and we're all hunky-dory with special relativity. You might say, well, what is this sufficiently small? Well, the idea is that a gravitational field, if it's absolutely uniform, then the laboratory doesn't have to be small. But if, as in all gravitational fields we know about, they're not uniform. And so if special relativity is to hold inside the laboratory, then the laboratory must fit inside a region of the gravitational field in which the field is uniform. And it's just locally, it's uniform. And of course, there would be small departures from special relativity, but they'd be quadratic or cubic in the size of the laboratory. Okay, so these are the two ideas on which general relativity is based, and basically everything else is a matter of turning some mathematical cranks, some of which can be confusing, and in many cases have the problem that that pretty soon one has several indexes and therefore many equations, and things can get complicated. But the basic ideas are simply use tensor equations, and special relativity holds in freely falling small regions, small laboratories. And in this first section here, I stressed the sense in which there's a physical reality, and it's described by our coordinates. And of course, our coordinates aren't particularly important. What's important is reality that we're describing in terms of these coordinates. And so the idea is that the coordinates of a point P is a physical point, and that the coordinates of the same physical point can be different. And what we'll assume generally is that the transformations that take us from the coordinates x prime to the coordinates x, and then back again from the coordinates x to the coordinates x prime, that these are smooth functions of x and x prime and so forth. Now, the simplest concept here is a scalar, and a scalar is a quantity that's the same in all coordinate systems. If it also depends upon the coordinates of the space-time point, then it's called a scalar field. Field is just a word for something that depends upon space, or depends upon, excuse me, space-time. All right, now, there's the notion of contravariant vectors and covariant vectors. And basically, these are very simple ideas. A contravariant vector is a vector that transforms like dxi. And in particular, if we change coordinates from x to x prime, then if we have dx in one coordinate system, dx prime is just a sum partial of x prime I partial xk dxk. This is just the chain rule of calculus. So this transformation defines contravariant vectors, and we write contravariant vectors with an upper index. And so a quantity is a component of a contravariant vector if it transforms like dxi. The coordinate differentials form a contravariant vector. A contravariant vector that depends on the coordinates is called a contravariant vector field, and it, of course, transforms the same way as the dxi's transform, like that. Notice that x super I is not a contravariant vector, and the reason is that x prime super I is an arbitrary function of x prime, is an arbitrary function of x. It's not a linear function of x. And so under a general coordinate transformation, the coordinate differentials transform linearly, but the coordinates themselves do not transform linearly in general. And now I just realized that I stupidly forgot to connect the iPad. And so I'm going to do that now by lowering the desk so that I can reach behind the iMac, connect the iPad, and see if I can get this working. So I'm going to notes, and there is the note that I started on the 16th. Now let's go back to raising the desk, and let me start QuickTime Player, File, New Movie Recording, iPad. Whoops, I clicked on iPad and nothing happened. All right, I don't know. Every time I try to get the iPad working on this, it's an adventure. So there I've clicked on iPad. One would think maybe I have to get, wow, what the hell was that? All right, I do not know. All right, that's that. That's working. That's clicked on that. Let me bring up, maybe I need to bring up notes. I don't know if, oh God. Well, I don't think that's helping. So I can write on the, let's see, conceivably it's occurring in some other place, but well, I don't know what's going on. Apparently this simply is not working. It's, I don't know, Apple changes its software every few weeks, and I'm sure that it increases their profits, but they're already the most valuable company in the world. I don't see why they have to screw everything up every few weeks. Anyway, of course, it probably is that I'm doing something wrong, but I don't know what it is. Let me just try one more time here. All right, I'm just going to have to use the mouse then to illustrate things. So anyway, the contravariant vectors are defined in terms of the differentials, and they transform linearly. Now, notice in special relativity, the coordinates transform linearly. Those are what we call the Lorentz transformations. But here we're talking about general relativity, and we're talking about arbitrary coordinate transformations, also called general coordinate transformations. And in this case, the coordinates, of course, since it's a general transformation, do not transform linearly. So here, what transforms linearly is simply the coordinate differentials. And they, under a general coordinate transformation, do transform linearly. Okay. Covariant vectors. Well, covariant vectors transform like derivatives with respect to the coordinates. And so if you change from x's to x primes, the derivative with respect to x prime I, is going to be a linear combination of derivatives with respect to x's, xk, times the partial of xk with respect to x prime I. This is just the chain rule. And any quantity that transforms like a partial derivative, is said to be a covariant vector. And if it depends upon the coordinates, then it's said to be a covariant vector field. I put in a new example. The new example is that the squared distance between points separated by dxi is given by gik of x, dxi, dxk, where gik is the metric of spacetime. Now, in a suitably small, freely falling laboratory, special relativity holds. And in its coordinates, the squared distance between points separated by the coordinates of the falling lab is ds squared, and it is dx prime dot dx prime spatial minus dx0 prime. dx0, of course, is c times dt prime. And that's then a linear combination here. Eta, of course, is the metric of ordinary space-time, which is minus 1, 1, 1, 1 diagonally. And the squared distance is a scalar because it's the same in every coordinate system. So in a general coordinate system with coordinates dx, or with the coordinates xi, then the metric of special relativity turns into the metric of general relativity, gik of x. Okay. Another example here is the gradient of a scalar. If you take the derivatives of a scalar field, so we have here in the other coordinate system, the prime coordinate system, we have the partial of b prime of x prime with respect to x prime I. Well, because b is a scalar, b prime of x prime is the same as b of x. So we take the derivative of b of x with respect to x prime I. By the chain rule, that's the partial of b with respect to xk times the partial of xk with respect to x prime I. So this gradient here is a covariant vector field because it transforms like a partial derivative. And of course, the reason it transforms like a partial derivative is that the only part of it that transforms at all is the partial derivative, b being a scalar. So tensors are things that transform like products of vectors. So a rank 0 tensor is a scalar. A rank 1 tensor is a covariant or contravariant vector. Second rank tensors are distinguished by how they transform under changes of coordinate. So you have a covariant rank 2 tensor, F with 2 lower indexes, and that is then when it transforms, it's, I mean, in the prime coordinates, it looks like this. You can have a contravariant one, looks like that, and a mixed one transforms this way. And you can go to higher tensors by extending these definitions to quantities with more indices. The rank of a tensor is also called its order or its degrees. So there are sort of 3 words that are used here. If S is a scalar field, its derivatives are covariant vectors and tensors. Rank 2 tensors, if you have 2 covariant vectors and 2 contravariant vectors, then the product AKBL is a second rank covariant. The product C upper M, D upper N is second rank contravariant. And then you can have these mixed second rank tensors. And now the transformation laws, of course, are linear. That is to say, the tensors have been, and vectors and scalars have been carefully defined so as to transform linearly under general coordinate transformations. And consequently, you can add tensors of the same kind and rank. So for example, if F and G are both second rank covariant tensors, the sum of the 2 is a second rank covariant tensor because F transforms with linearly in one way, G transforms linearly in exactly the same way, so H transforms the way F transforms, and this is also the way G transforms because they transform the same way. Now, just as in special relativity, people got tired of writing summation symbols, and so if you have a monomial with 1 upper index and 1 lower index, you sum over that index, and in general, it's sum from 0 to 3. If you're talking about embedding spaces, then it could be sum over more indexes or indices. The rank of a tensor is the number of its uncontracted indexes or indices. And here, what I forgot to say here is that this thing that's a sum, either explicit or implicitly via Einstein's sum convention, this is called a contraction. And it's I guess the term is used because the index I is no longer functional. That is to say, when this A lower I, B upper I, this thing is a scalar. So when you change to a different set of coordinates, this index, it acquires a prime perhaps, but it's not, it doesn't transform because it's just a scalar. It's the same in any coordinate system. So A lowercase c upper L, that's a mixed second rank tensor, but A lowercase c upper k is a scalar. And the way you see it's a scalar is that A transforms this way, C transforms this way, and now you sum over k, but then by the chain rule, that was just partial of XL with respect to XM. That's, of course, Kronecker delta, 1 if L is M and 0 otherwise, no hidden minus signs, and so that's AL C upper L. Similarly, this thing is a scalar, and in fact, this is basically E squared minus B squared. What happened here? We just lost a page. Where was I? Yeah, I was here somehow. Oh, everything's so touch sensitive. So this thing is, in electrodynamics, it's E squared minus B squared. And it's a scalar, and that means that it's a suitable, something that you can, not only is it invariant, the same in all coordinate systems, but you can also use it as a term in the action of the theory and derive the equations of motion from an action principle. The Kronecker delta, the summation convention says that partial xi, partial xk, partial xk, partial is just this, which is that, which is what I used in a previous example. I guess that example should have come earlier. Well, okay, so I'm just writing a note to myself. So this is this summation convention explains why this thing is the Kronecker delta. And the repeated index K disappears in this contraction. The Kronecker delta is a mixed second rank tensor, but it transforms in such a way that it's invariant under changes of coordinates. So it's kind of both a scalar and a second rank tensor in a sense, in these senses. Now, examples of tensor equations, as I said, one of the two ideas that underlie general relativity are, one of them is to use tensor equations, and examples of tensor equations, well, some of them occur in electrodynamics because classical electrodynamics is so close to reality that some of its equations hold in general as well as special relativity. So in particular, Maxwell's homogeneous equations can be written this way, and these equations are invariant under general coordinate transformations. We'll discuss that later. In these sections. And they follow in the language of forms from this Bianchi identity, which we saw in chapter 12. The inhomogeneous equations look like this. By the way, notice there are 4 of these because you see you have 3 indexes, I, J, K, that occur in each of the 3 terms. So you're leaving out one index. But that one index can have 4 values, 0, 1, 2, or 3. That's why there are 4 equations. Maxwell's inhomogeneous equations, such as the divergence of E, or in vacuum, in the microscopic form, the divergence of E is proportional to the charge density rho. And there's another one that relates the magnetic field to currents. These can be combined, these are combined or can be combined into 4 generally covariant equations. And here little g is the absolute value of the determinant. And then we take the square root of the absolute value of the determinant of the metric. This metric is the metric that showed up earlier here. The metric tells you what the invariant distance is between 2 points separated by the dxi's. So if we get back to where we were, Well, I am a little confused. I think I was basically here. Yes, so these are generally covariant tensor equations. Now, of course, these inhomogeneous equations do change going from special to general relativity. In special relativity, this G is just 1 and square root of 1 is 1. And so this equation is simpler. In special relativity, general relativity, there's a little, the G is the determinant of the metric, which is a 4x4 matrix. And then you take the absolute value. Some people don't take the absolute value, and then they have to have a minus sign here. It seems to me a little bit dumb. These are generally covariant tensor equations. And notice the very small change from ordinary electrodynamics to electrodynamics in general relativity. We'll discuss these in a later section. Einstein's equations. Here we've got the energy momentum tensor, Newton's constant, and here's the scalar curvature and the Ricci tensor, which is a sort of trace of the curvature tensor. Anyway, the curvature of space-time is on the left-hand side, and it's related to it's proportional to the energy momentum tensor, and the constant proportionality, though, has a very weak constant, Newton's constant, divided by the 4th power of a very high speed of light. And we take them up in section 36, which I think we'll get to before class ends, before the course ends. And so the idea is if you can write a physical law in one coordinate system in the form of a tensor equation, G upper JL of X equals 0, then in any other coordinate system, it's G prime IK of X prime equals 0. So it's the same equation. And that if this equation is true in the X coordinate system, then this one is true in the X prime system, because this thing is a tensor, here in this case, contravariant rank 2, and so it transforms this way. On the other hand, these guys are all 0, so this one's 0. By the way, notice that you can take any equation and write it in the form something equals 0. You just subtract everything on the right-hand side. That reminds me of an incident when I was a graduate student. A very accomplished professor was saying, and this result is true because it follows from this equation, which is of the form something equals 0. And a friend of mine who is very bright was sitting, I think, in the front row, and he said, yes, but professor, every equation can be written in the form something equals 0. And that was one of the very, very few times that that professor was upstaged by a student. Anyway, so the point is that physical laws remain the same if they're written in terms of tensors, or equivalently in terms of forms. And so a theory written in terms of tensors or forms is equations that are true in all coordinate systems if they're true in any particular coordinate system. And so only such generally covariant theories have any chance of being correct, because we never know which coordinate system is the right system in some sense. Okay. Now, as I said, the other idea of Einstein's that lies at the basis of general relativity is sometimes called the equivalence principle, or the principle of equivalence. And it's what I said earlier, that if you have a sufficiently small lab that's falling freely, then special relativity applies inside. And so you can write ds squared as a to JL, where this is the Minkowski metric, the metric of flat space-time. And well, what are these dx primes? Well, these dx primes can be related to the dx's of any other coordinate system in this way. And so, since ds squared is invariant, this thing is the metric. And so the metric in the arbitrary other coordinate system, or the metric in every other coordinate system, gik of x, is related to the coordinates of the freely falling system by this expression here, in which 8 is the Minkowski metric, or the flat metric of flat space, -1, 1, 1, 1. Here are two definitions: symmetric and anti-symmetric tensors. It's symmetric if it looks like that. It's anti-symmetric if it looks like this. The Maxwell field strength, the thing that has 4x4 with E and B, this is anti-symmetric. And anti-symmetry just sneaks into physics in many, many places. And in fact, it plays a role in physics that it's extremely general. It's a very great role. It occurs all over physics. And in particular, we're all, although we like to think in terms of bosons because somehow bosons don't have any minus signs. The fact is, we're all made of fermions, basically, apart from the gluons. And so the anti-symmetry is just built into everything in physics. Okay, I mentioned the quotient theorem last time, and I'll just state it again since we kind of went through it last time. If B has unknown transformation properties, but what we know is that BA suitably contracted with all tensors A of a given rank and kind, actually a particular rank and kind, then B must be a tensor. So for example, if A is a contravariant vector and B lower j, A upper j is invariant, then it turns out that B lower k has to be a covariant vector. And then there's this notation for derivatives. I often use this comma notation in the later sections of the book, just because it's you save a lot of space in it. But I don't know whether this is so smart a notation. I don't really know. Anyway, it's what I used. So f sub comma I is the ith derivative of the partial of f with respect to x upper I. If it's f comma ik, then you get the double derivative. And the same thing for tensors. Semicolon are going to denote covariant derivatives, which I hope, I think we'll get to today. So basis vectors and tangent vectors. Well, as I said earlier, a point in space-time is physical, and so it's a scalar in that it's the same point in any coordinate systems. So P of x is P prime of x prime. That's a physical point, and it doesn't depend upon our coordinates. Our coordinates depend upon the way we get out of bed that day, but not points in space-time events exist independently of our coordinates. So its derivatives the derivative of a point with respect to the coordinates, they form then a covariant vector. And the reason is that P is a scalar and the partial derivative is a covariant vector. And so if we can define then a basis vector, which is how the physical point moves when you change the ith component of its coordinate, x. And these things I call basis vectors. They form a covariant vector. And the reason is that they're partial in a prime system. It's partial of P prime of X prime with respect to X prime I, but P is physical, so it's unchanged. It's a scalar, so that's partial P of X with respect to X prime I. And that then is, by the chain rule, partial of P with respect to XK, partial XK, partial X prime I. And that this thing is the basis vector. And so we have just these coefficients, but that tells you how, that's the definition of a covariant vector. So small changes in the coordinates, of course, lead to small changes in the point. And covariant vectors then are a basis for the space-time point, for space-time at the point. So in other words, we go from P to a slightly different point by an amount EI dxi if we change xi. And these things are said to be, these things are tangent to the curved space-time at the point x, so they're called tangent vectors. And I'm going to skip that sentence, and I may even delete it. Now, I want to discuss the metric tensor in two ways. First, I want to talk about the metric tensor for purely Euclidean spaces, for what are called Riemannian spaces or Riemannian manifolds, and then talk about semi-Euclidean or semi-Riemannian manifolds. The difference is that in the first case, we're talking about space, and in the second case, we're talking about space-time. So let's look at space to begin with. And a Riemann manifold of dimension d, well, it's a space that locally looks like d-dimensional Euclidean space, and that is smooth enough so that the derivatives that define tangent vectors exist. So the surface of the Earth, for example, looks flat at distances less than a kilometer. And in fact, some people actually think the Earth is flat, and that the theory of the spherical Earth is some liberal lie that people are foisting upon an unsuspecting population that's trusting science too much. Anyway, the surface of the sphere, of course, can be embedded in flat Euclidean three-dimensional space. And on the other hand, locally, the surface of the sphere locally looks two-dimensional. So that's basically the idea. And now something that has been proven by a long time ago by Nash is that every Riemann manifold can be embedded without change in shape in a Euclidean space of suitably high dimension. So if you have a Riemann manifold of dimension 3 or 4, you can embed it in a Euclidean space of at most 14 or 19 dimensions. This was something shown by Gunther. So this, but the thing to think about though is the surface of a sphere can be embedded in three-dimensional Euclidean space. That's basically what we're talking about. The surface of the sphere, curved two-dimensional space, a curved Riemann manifold. We embed it in a three-dimensional Euclidean space. It's Riemann because the sphere is Riemann because locally on the surface of the sphere, it looks flat. And just as the surface of the Earth looks flat at ordinary distances, the distance you can run without getting tired, well, that distance it looks flat. Now, if you then take these basis vectors and just do an ordinary Euclidean dot product, you get the metric of the Riemann manifold. It's automatically symmetric. This dot product, though, I have this alpha index goes from 1 to n. So for example, the case of a sphere, we would have I and k would go from 1 to 2, but alpha would go from 1 to 3 because we're embedding the sphere in three-dimensional space. And these tangent vectors are tangent to the sphere, but they're vectors in three space. So they're three vectors. Because they're covariant vectors, the metric tensor, which is as I said, the dot product of these basis vectors, this transforms as a second-rank covariant tensor. And the squared distance, well, what is it? It's dp dot dp, and so that is the tangent vectors give you the metric of space-time, and what you have left over is dxi, dxk. And so by measuring the distance between nearby points, one can determine the metric of a Riemann space in terms of whatever coordinates it is that you choose to use. So there's this sort of reciprocal relationship here. So the example is the sphere S2 and E3. If you have polar coordinates, if the sphere is of radius r, then it's r sine theta cosine phi, sine theta sine phi cosine theta. You take the tangent space by taking the derivative vector theta and phi, and you get these two vectors. And the metric then is formed from the dot product of these metrics, of these basis vectors, and you get this 2 by 2 matrix. It has a determinant equal to this. ds squared then is, since e theta dot e phi is 0, it's just r squared d theta squared plus r squared sine squared theta d phi squared, which is here I'm computing d theta squared. E theta dot e theta is r squared, and e phi dot e phi is r squared sine squared theta. And if you want, you can make this funny change of variables, and then ds squared takes this form. The reason I'm writing this is that a common way of writing the metric of our universe or our pocket universe is very much like that. Okay, I think I'm going to skip those two and go now to discuss the kind of universe we actually have, which is one that's as far as we know, it's a semi-Euclidean or semi-Riemannian manifold. And what does that mean? It means that locally it's semi-Euclidean. And what does semi-Euclidean mean? It means it's a flat space-time like the space-time of special relativity. It has one or more time dimensions and several space dimensions. And so the metric then, in terms of these basis vectors, because it's semi-Euclidean, you'd have u time components and d minus u space components. And that's how we'd have the dot product of the basis vectors, and that would give the metric of space-time. And the squared distance ds squared is then dp dot dp, of course. And now when the ei dots ek, you get gik of x, but this gik is no longer necessarily positive. And in fact, it can be negative. Actually, even in a Riemannian manifold, you could have gik negative. The basis vectors don't need to be orthonormal by any means. Okay, so here's a couple of examples. Here are a couple of examples. Actually, it's just one example of a semi-Euclidean space and a semi-Riemannian space. So this hyperboloid H2, radius r, you can embed it. It's a two-dimensional space, or space-time. You can embed it in a three-dimensional semi-Euclidean space-time. I here took the metric to be 1, 1, minus 1. So instead of minus 1, 1, 1, 1, we've got 1, 1, minus 1. And the points obey this equation for this hyperboloid. It's x squared plus y squared is z squared minus r squared. And so in other words, the z component has to be greater than, z has to be greater than plus r or less than minus r, so that this thing is positive here. And so the thing looks like, it's actually a little bit silly. It looks like that. And so it sort of lies in a we have z. If z is coming out of the screen, then the thing looks like that. The tangent vectors look like this, and the metric is this. And we can also make this funny change of variables, and then the metric looks like that. If instead you use the same labeling of the points and the same equation, and you use the metric 1, 1, 1 of ordinary Euclidean space, then you'd have a hyperboloid that's not maximally symmetric. This one here, like the sphere, is maximally symmetric, which basically means that when you make a transformation, the metric changes as little as possible, or you have the most possible symmetries. And on the sphere, of course, you can rotate the sphere. If you can rotate in an arbitrary way about the center of the sphere, and the sphere doesn't change. With this hyperboloid, you can rotate it about this axis, and well, with an ordinary hyperboloid, you can still rotate it about the axis. With this one, I guess it must be that you have an extra symmetry, and I just don't quite see the extra symmetry, I must tell you. So let me just write a note to myself. What is the extra symmetry? I'm not sure what that is. Anyway, the inverse of the metric tensor. We don't really need to talk about this. The metric's a non-singular matrix. That's an exercise. So it has an inverse. And the inverse we write as G upper IK. So G upper IK, GKL, it just gives a Kronecker delta. And of course, the inverse in prime coordinates is G prime IK. The Kronecker delta then looks like this. And here I've written G prime. Well, G prime is related to G this way. we multiply both sides this way, and we see that G prime with upper indices has to transform this way, which of course is the way way we expect something with two upper indexes to transform, namely as a second rank contravariant tensor. And remember, in special relativity, we use eta to raise and lower indexes. So too, in general relativity, we use G to raise an index or G to lower an index. And I meant several times to make this bigger, and I kept forgetting. I don't see anything on this chat, the chat screen. So feel free to say something on the chat screen, especially if you have a question. By the way, in order to ask a question, one has to have a basic understanding of what is being said. And so the fact that you might ask a question doesn't mean that you're slow or retarded or stupid. In fact, it means you're smart enough to know enough to ask a question. So, so people asking questions, the students asking questions are generally the ones who are more on top of the material. Of course, somebody might be an expert, totally bored, and not ask a question for that reason. So we've the way in which one way of making a scalar is to take two contravariant vectors, multiply it by the metric tensor, and this lowers an index, and now we have something that's a scalar. Similarly, if you have two covariant vectors, multiply by the metric, you get another scalar. So that's a way of making scalars. Now, there's this term space and space-time. Space-time is kind of a clumsy word, and people often use space to mean either space or space-time, and I'm going to do that. I'm often going to use space when I mean space-time, because it's just sort of tedious to say space or space-time. So dual vectors. Well, we've got these basis vectors. We multiply them by the inverse metric tensor, we get the dual vectors. These obviously then are contravariant, or at least they pretend to be contravariant vectors because they have an upper index. And they're orthonormal to the tangent vectors, and you can see that because G upper I is GIK EK, and the dot product of EK with EK is GKL. And now you sum over K, this is the inverse of that, so this is the Kronecker delta. So these cotangent vectors are basically orthogonal to the basis vectors. They're said to be dual vectors. Now, this dot product here, let's keep in mind what this dot product is. This dot product is the dot product of the space or space-time. So in particular, if it's a space, then all those terms here, all the coordinates of EI and the coordinates, I'm sorry, over here, the coordinates of EK, the coordinates of EL, these are all just multiplied together. Whereas if it's a space-time, then in this dot product, you have a minus sign on any of the time components. So there are hidden minus signs in this dot product if we're talking about a space-time. And this is true, of course, in special relativity. If we have two time-like vectors and we take the dot product, we're going to get something that is going to be negative. So these dual vectors are sometimes called cotangent vectors, and some of the people call them tangent covectors. Anyway, if we lower the index we then have another Kronecker delta and we get back to EK. So this is just another example of the fact that G can raise and lower. The inner product of two of the cotangent vectors is, well, by definition, it's GIK on the E lower k. This guy here is a Kronecker delta. So it's just G with the upper indexes, is the inverse metric. So it's rather cute. The dot product, or dot in this generalized sense, which may have time components with minus signs, this dot product of two cotangent vectors is the inverse metric. It's all quite cute. And these outer products here are the identity matrix, and that's because EK dot. And this is in the book, I didn't have a dot. It's not wrong without a dot, but I should have put in a dot. Anyway, this dot tells you that there may be minus signs. Anyway, the dot product is definitely the Kronecker delta, and so that's EI. And the P looked like, written this way, again with a dot product delta K, I, K, EI. So P hitting lower or upper, P on tangent vectors or cotangent vectors just is the identity matrix. All right, now this notation, which I think demystifies general relativity, but I don't know, maybe you think it mystifies it. I think it, the nice thing is that we sort of imagine that whatever the space or space-time is, it's embedded in a bigger one that is just an ordinary Euclidean or semi-Euclidean space. Anyway, let's talk about the covariant derivative of a contravariant vector. And the idea here is that we want this thing to transform like a vector, in fact, like a partial derivative. We want it to be a covariant vector. So we want this derivative to be a covariant vector. Now, what we're going to do is we're going to write V as a scalar, and we make it a scalar by taking the summing the contravariant vector with the covariant basis vectors. And so this thing is a scalar. So this automatically is a covariant derivative. So we basically are home free. But now if we write V as VI-EI, we see the derivative acts on the VI and the derivative acts on the EI. And so now what we have is that this, now this thing is a covariant, this is a covariant vector, but the covariant vector that, or the covariant derivative, I should say, is written this way. And sometimes one writes it as a capital D sub L. Sometimes one writes it as a semicolon. Where did I write it as a semicolon? There's it written as a semicolon. And the point is, it is the dot product of the dual vector EK with this covariant vector. And so that means we have something that is a mixed second-rank tensor. And so EK dotted into this, well, EK dot EI is going to give a Kronecker delta. And then EK dot this, well, that's something else that we have to look at. And so the covariant derivative that's normally written is DL on VK. It is then an ordinary partial derivative plus this funny thing here times V upper I. And now what is this? Well, this thing is what is called the affine connection. That's, I think, the better term, because the other term is a Christoffel connection or a Christoffel symbol of the second kind. And you have to remember, how the hell do you spell Christoffel? And whereas affine is just A-F-F-I-N-E, and that's a lot simpler. Also, affine has a meaning, and it relates to tangent vectors that don't have the same origin. And so in other words, we were talking about derivatives of the point P at slightly different points. And so at one point, you'd have that point X might be the origin of the tangent space at X, but then at some other point on the manifold, you'd have some other point, and that point would be the origin for the flat tangent space there. So that's why it's called affine. Anyway, it is the dot product of the cotangent vector with the partial derivative of the tangent vector with respect to a coordinate. Okay. And another notation for this thing is V upper K lower semicolon L. And so this is the way it's written. I'm following the notation of Misner, Thorne, and Wheeler. Some other people interchange L and I, but the difference between gamma K IL and gamma K LI in general doesn't matter, because in standard general relativity, they're equal. Now, of course, in more sophisticated or less. Okay. All right. Somebody just asked, what is affine? The idea is, as I said just a moment ago, if you look at a sphere, you look at the North Pole. At the North Pole, you have a tangent space. The origin of that tangent space is the North Pole. You go to some point on the equator, you have a tangent space, and that point on the equator, that's the origin of that tangent space. So that's the idea, that an affine connection relates tangent spaces, and the tangent spaces don't have a common origin. They have their own origins. Anyway, well, the actual meaning of the word, the etymology is not important, because it's just a label for this thing here. And one thing that you can do is you can take the derivative of the Kronecker delta. And what is the Kronecker delta? Well, it's the dot product of, one way of writing it is the dot product of a dual vector with a vector. And so that you get these two derivatives. And this is a very useful formula, because this tells you that this thing is minus that thing. This is the thing that's the affine connection that showed up here. And this thing is something that will show up presently. And when we find it, we'll say, oh, it's just minus the thing we had before. And it follows that the covariant derivative of a cotangent vector vanishes. So that's this. Now, okay, there are a lot of indexes here. Let me just cut to the chase here and just tell you what the bottom line is. The bottom line is that the affine connection transforms, I don't know why we write it as this horrible capital Greek gamma. It's, I think, a horrible notation. Anyway, this affine connection thing transforms this way. It's not a tensor because it has this inhomogeneous piece here. And so that means it's more like the gauge field of electrodynamics, because when you make a gauge transformation in electrodynamics, your gauge field transforms inhomogeneously. You get a minus the derivative of a scalar. And this thing is a derivative term here. In fact, I should probably try to write it as a derivative, the way I've written it here. Well, it's an inhomogeneous term. Maybe it's not a derivative of a scalar. Let's think about that. Anyway, it's, okay, I'm going to skip through the rest of this and get us to the covariant derivative of a covariant vector. And here what we have is we once again take the covariant vector and we multiply it by a dual vector and we get a scalar. And so we know this is going to be a covariant vector, but when we differentiate it, we get two terms, the derivative of VK, but we also have the derivative of the cotangent vector. And now we do what we did before, kind of, we take the dot product with a covariant basis vector EI, and that gives us a Kronecker delta here, and then it gives us something funny here. And the Kronecker delta then gives us this VI comma L, the Lth derivative of VI. Then we have this funny structure here. Well, this funny structure is the one that we saw just recently. It's the one that I said was going to be useful, namely that this thing is minus that thing. So this thing is minus gamma. And so this thing here is minus gamma. So the rule for the covariant derivative of a covariant vector is the ordinary derivative, a minus sign, and then you sum over the indexes of V. Well, V has a lower index, so gamma has to have an upper index. And then you've got your ILs, and you can do it IL or LI. It doesn't really matter because, as I said, in standard GR, they're the same. And the covariant derivatives of tangent vectors also vanish. Covariant derivatives of tensors, well, the ordinary derivatives of tensors work like this. You just take the ordinary derivative, it just looks like that. So what about the covariant derivatives? Well, the covariant derivative, it's going to be the covariant derivative of the one plus the other times the covariant, plus the one times the covariant derivative of the other. And you can combine these two as the ordinary derivative of the product, and then you get two affine connection terms. And so the general rule then for a general tensor is that the covariant derivative of the second rank tensor is the ordinary derivative plus two terms where you have the gamma, where you have the affine connection. And so some examples of this are the ordinary derivative of a mixed tensor looks like this. The covariant derivative is like this. You take the covariant derivative of the first one, the covariant derivative of the second one. Notice the second one, because it's covariant here, you get a minus sign. And so you have something that looks like this. And if you take the ordinary derivative of two vectors, you get that. The covariant derivative is, well, you have the covariant derivative of the one, the covariant derivative of the other. And that's, since they're both covariant vectors, you have two minus signs, and it looks like that. So these are other ways of doing the thing. I don't. By the way, the mathematical term for this sort of thing is a derivation. So a derivation is a generalization of a derivative. And the idea of a derivation is that the derivation of a product is the derivation of one times the other plus the one times the derivation of the other. And now, if you apply these rules to the metric tensor, well, what is the metric tensor? Well, it's whatever this generalization of the Minkowski tensor is, times the EI alpha EK beta, and you take the covariant derivative here, well, that's going to be the covariant derivative of one basis vector and the covariant derivative of the other basis vector. But we just saw the covariant derivatives of basis vectors vanish. So the covariant derivative of the metric vanishes. That's important, that the covariant derivative of the metric vanishes. That makes a number of things simpler than they would be otherwise. Well, I see that we're out of time. Does anyone want to write a quick question on the chat board? Because I certainly have time to, I mean, I can hang around and answer it. All right, well, I'm going to hold class tomorrow, and maybe what you can do is, if you want to, is you can put together some questions and we can have lots of questions tomorrow. In any event, I've been recording this, I think, and so I'll put it on YouTube. So I wish everybody a nice evening, and you know, try to get a booster shot, for God's sakes. I've had 3, and not 3 boosters, but I've had three Moderna. I urge you all to get 3, to get triply vaccinated. Yeah, thank you. Yes, COVID is increasing in New Mexico, and I don't quite know why. I think it's probably that the Native Americans are still getting the short end of the stick. And well, what are we going to do? This country was founded upon injustice. We've got to somehow rectify that. All right, I'm going to say goodbye to everybody. I'm going to stop recording. See you all tomorrow, I hope. Thursday, no class Thursday. That's Thanksgiving.